This is video number 15 in our series Topics in Quantum Mechanics. The playlist for all the videos that we're going to produce in this series is not on YouTube. It's at the website at digital-university.org. Okay, in the last video we had discussed the general formula for a Fourier transform pair, and that's these two equations right here. And then we use these equations to derive the Fourier transform of the Dirac delta function, and we ended up with this expression. So what we have now is an integral expression for the Dirac delta function. Now what we want to do in this video is apply this knowledge to the eigenfunctions of the momentum operator. Before we do that, let's ask ourselves, what would happen if we took x minus a and divided it by a constant, say by h bar? If we did that, then over here on this side we would have this. And how do we know that? Because it was in the video titled Properties of Dirac delta function. What we showed is that if we have said the Dirac delta function just of x, but then we divide it by a constant, divide that by some constant, say we'll just call that constant a, that is equal to a times the Dirac delta function of x. So if I had the Dirac delta function of x minus lambda divided by a, that would be equal to a times this Dirac delta function. Okay, now what we want to do is go back and talk about the eigenfunctions of the momentum operator. And in video number 12, we determined that the eigenfunctions had this general form. And again, when we derived this, it was for a particle moving along the x-axis. And for all of our first 20 videos or so, we're going to be restricting our analysis to just particles moving on the x-axis in one direction. Now, A, well, remember that P was the eigenvalue for the momentum operator. We started with this momentum operator operating on some ket vector, we'll just call it B, is equal to just some constant times that ket vector. That's the definition, of course, of an eigenfunction, eigenvalue relationship. This is just some constant number. Well, now when we apply it to a wave function, like we did in video number 12, we had this kind of expression. And again, we're taking the derivative of the wave function just with respect to x, because we're just working with the particle along the x-axis. And this is the eigenvalue corresponding. And then this right here, that is the momentum operator. And this is the corresponding eigenvalue. And then we had a very simple differential equation that we integrated and got this expression. And A was just simply, well, it came out from being a arbitrary constant of integration. So now let's label this. Say this will equal, say, psi px, because this is our position here along the x-axis, and this is a the eigenvalue corresponding to the momentum operator. So we have P and X here. So we'll label it like this. Now, if we had, say, a psi P prime of X, that would equal A. Then we have E to the I P prime for H bar X. Now remember, in quantum mechanics, we discussed this in several different contexts now, that the functions you work with, you want them to be square integrable. That is, if I have a particular function, say phi, when I multiply it by its complex conjugate and integrate, we want this to be equal to some well-defined value, just say less than infinity. Whether we're integrating from 0 to infinity, that is going anywhere along the x-axis, or whether it's, say, just in some region along the x-axis, a to b. So what we're saying is that we want the inner product of the functions to be well behaved. Well, what happens if we take then the inner product of our momentum eigenfunctions? And this has always been a sticking point in the past videos, but now we have the tools to look at it more closely. So what we want to do then is take the inner product, say of this psi P prime of X with psi P of X. And as we discussed now in the previous videos in our series, this is equal to the integral minus infinity to plus infinity psi P prime of X. We take that the complex conjugate of it. This is now a bra vector. And also we're going to have A times A, two constants. Those would be at the outside. And then we're going to have the complex conjugate of this. So we have E to the minus I P prime H bar X times this, E to the I P H bar X dx. So this is what the inner product is then of two eigenfunctions of the momentum operator. We have this expression, and it looks like we can simplify this. This equals a squared, the integral E, then we'll have I P minus P prime divided by H bar X dx. Multiply these together, we'll just add the exponents, and we'll have P minus P prime Ix over H bar. Okay, so this is what the inner product of two momentum eigenfunctions are. There is no way to evaluate this integral in terms of, for lack of a better word, I'll say regular functions. But let's compare this integral right here to this integral right here. In fact, let's do this. Let's erase all of this space. We'll come back to this. We'll erase this for now, but we won't forget it. What we want to do is erase this space and put this integral side by side this integral. Remember, in this integral right here, this is the inner product of two momentum operator eigenfunctions. Okay, let's make some room. So we have a squared, the integral from minus infinity to plus infinity, e to the I, p minus p prime, divided by h bar times x dx. And that is the inner product of two different momentum operator eigenfunctions. Okay, let's compare these two integrals now. Here we have x minus a over h bar k dk. Here we have x dx. And we have here I and h bar. So very similar, except we have a mistake here. This should be 1 over 2 pi. Okay, now it's correct. Well, then imagine that if this integral right here, for the moment, let's just imagine that it was divided by 2 pi. This integral here divided by 2 pi, that would then be the Dirac delta function of h prime of p minus p prime. Except this integral here is not divided by 2 pi. So we're going to have 2 pi times this. And we also had a squared here. So we have a squared here. So what we finally have is that the inner product of two momentum operator eigenfunctions equals this expression. Now remember what a was. That came from an arbitrary constant of integration, so we can let it be anything we want. So if we let a can't see that very well, we'll write it down here. Let a equal 1 over the square root of 2 pi h. Then these just cancel. Remember, this is completely arbitrary, so this is completely legitimate. We can let it equal anything we want. So we do that, and here's the expression. So finally now we have an expression for the inner product of the eigenfunctions of two momentum operators. Well, the first thing we can see is that this is not square integrable. And what we said earlier is that in quantum mechanics, with the functions that we're working with, say phi prime, phi dx, we want that to be equal to some nice well-defined value. We'll just put these limits on. Well, that's not what this is. So we also see now that the inner product of these eigenfunctions is not square integrable. Okay, we also have this situation that the eigenfunctions of the linear momentum operator, those are Dirac delta functions. That is an eigenfunction for the position operator x prime. So here, for the position operator, we have its eigenfunctions are Dirac delta functions. Now here, for the momentum eigenfunctions, now we have this. that is the eigenfunction for the momentum operator. I'm leaving a out now. Well, we can know a is actually divided by 1 over the square root of 2 pi h. That's what a is equal to now. So there's the eigenfunction for the momentum operator, but when you take their inner product, out comes these Dirac delta functions. So we're back to these expressions again. So what we're going to do now in the next video, I don't think we have time to fully address this issue in this video. So in the next video, what we're going to do is discuss the Dirac normalization process of these eigenfunctions here. And also we'll talk a little bit more about the eigenfunctions corresponding for the position operator as well. And remember, in each case, for the momentum operator, the corresponding eigenvalues aren't just discrete numbers, they're a whole continuous spectrum of numbers, and that was also the same for the position operator. Its corresponding eigenvalues were not well-defined discrete numbers, but rather a whole spectrum of numbers. So, come back, join us in the next video, and we're going to consider all these issues together, and finally then we will be able to discuss the Dirac normalization of these momentum operator eigenfunctions. So come back, join us for that video, and finally we can wind up this discussion.